Hello guys, so I want us to look at some speed time graphs, mainly focusing on describing the motion. Right, so usually a speed time graph has a vertical axis that represents the speed of an object, how the speed of an object is changing. So the vertical axis is for speed, right? This is normally in meters per second, and then the horizontal axis is for time, mostly in seconds. So when it's empty like this, it means there's nothing taking place. There's no motion in this particular place. The object is probably at rest. So we can just highlight that the object is at rest. In other words, there's no motion here. Okay. And then once we have a graph with lines inside, for example, let's say we have something like this. Right, speed here and meters per second, and then time on the horizontal axis in seconds. Right, once I have a straight line in this nature, what it means is that this object is actually moving. So you can say the object is moving with a constant acceleration. Right, why do we say we have constant acceleration? First of all, we need to understand how acceleration is calculated, right? So basically, acceleration is actually the change in speed. Normally we use v over the change in time. So if you look at this expression, you realize that this is simply the gradient of the line. That's the gradient of the line. So if I decide to calculate the gradient of the line, I have to choose 2 points on the line. For example, I can choose a point here and a point there. Right, remember, maybe from mathematics you need that triangle. Okay, so of course this point here is associated with a certain t value. We can call it t1, and then this one is associated with another point t2, and then vertically there we have a speed, maybe v1, and then that one we can call it v2. All right, so then when you're now calculating your acceleration, I know you're familiar with the v minus u over t, but you can always write v2 minus v1 over t2 minus t1. Please don't get me wrong, this is still the same as v minus u over t, right? Where v is the final speed, u is the initial speed, and t is the time taken in between. So if I calculate the gradient using those points, one can actually decide to use maybe another point, this point here, and maybe another point up there, this one here and another one up there. Still I have the gradient. I'll still get the same value. So the rate at which the speed is changing over time is constant. It doesn't change. So at the end of the day, we end up having the same acceleration for that particular period. Okay, so once you have a straight line like that, then it means we have a constant acceleration. The other term that you can probably use for constant is uniform. Okay, instead of using constant there, you can use the term uniform, just like when we wear uniforms in school, isn't we all look the same? So that's what that term means. So once you have anything, a straight line like that, it doesn't matter the steepness or the slopeness, but at the end of the day, as long as it's a straight line like that, it means it's uniform acceleration. It may just differ that maybe some of them have a bigger gradient, some have a smaller gradient. Of course, if I'm to compare, maybe I call this line number 2. This one is less steep, okay? Less steep, meaning that we have what? A less acceleration. less acceleration compared to the first one. If I would have another line up there like this, then this one is more steep with the greatest gradient, more steep. Okay, so it has greatest acceleration. If I'm to compare, this is line number 3 probably, greatest acceleration. Right, but all these accelerations are just constant. Okay, right, and then if it happens that I have a line like this one, right, I'll draw another one because we have different scenarios. Okay, this is speed in meters per second, and then I have time in seconds, right? So if it happens that the line starts from the top going down like that, it's a straight line, right? Now this is uniform or constant deceleration, right? The other term for deceleration is retardation. Retardation, right? But we rarely use this term. We normally use deceleration. So if you calculate the gradient of this line, the gradient will be equal to delta V over delta T, and it's going to be negative gradient. All right, so since it's negative gradient, so that means it's actually negative acceleration, because remember that acceleration is equal to that. So in actual fact, when you're calculating deceleration, you calculate acceleration, but it's going to come out negative. And once you get a negative answer, the moment you write deceleration, you remove the negative answer, you don't put it. The same thing applies again if you're calculating gradient. You choose 2 points, just like the one at the top there. Any line that is straight and going down like that on a speed time graph, it means that that object is moving with a constant deceleration or uniform deceleration. All right. Right, and then once I have a line like this one, so the reason why I'm giving you these separately is because I want you to understand the segments. All right, the line segments, especially when you're given a whole full graph, you must be able to tell that, okay, at this point I have to describe it this way. Then I have time here in seconds. Any horizontal line, it means we have constant speed here. Remember, the word constant means uniform. So in this case, you realize if the speed was 20 here for all the times along, it means it's not changing. And once the speed is not changing, it means there is no acceleration. No acceleration. We must be able to link up these things again. Remember, A is equal to delta V over delta T. So if there is no change in this guy, if the change in speed is 0, then it means the whole thing becomes 0. So any horizontal line on a speed time graph represents motion that is not changing speed. The speed is not changing. Right, you come across situations where you'll have graphs like this. Right, let me squeeze them so that I don't waste my space here. Right, this is speed, right, in meters per second. Then this is time, the side, in seconds. You might come across things like this, right, or something like this. Right, these graphs, you must be careful the way how you describe the motion when you come across them. Okay, so when you look at these two graphs, you realize that in both cases speed is increasing while its time is also increasing. But both of them, they are curves. So the fact that they are curves, it means there is non-uniform acceleration in both curves. Non-uniform acceleration, but we must be very careful how this acceleration looks like, right? So if you are to calculate acceleration on a graph like this, you don't calculate acceleration for the whole journey. You actually calculate acceleration at a specific point. You calculate acceleration at a specific point by drawing a tangent. For instance, let's say maybe we have t1 here and maybe t2 there. If I say calculate acceleration when t is equal to 1, it means that I'll go all the way up to this point, which is in line with t1. Then at that particular point, I'm going to draw a tangent there. At that particular point as well, I'll have to draw another tangent there. Right, that's not a tangent. Tangent has to be just outside the curve. So I have to draw tangents at specific points. Now, when you look at these lines, the reason why I picked two, I wanted to make sure you understand how you describe this particular one. So this one is actually more steep. Let me just say steep. This one is steep, right? And this one is less steep. This one is less steep. What does this tell us? It means that we have actually more acceleration here. More acceleration, and then we have less acceleration there. All right. So what does this bring us to? When we highlight that this is non-uniform acceleration for this particular graph, we have to indicate that the acceleration is actually decreasing, but in a non-uniform manner. All right. Unlike the second one, if you consider the second one, maybe when t is equal to 1 there, you realize that you have to draw your tangent just outside here. This is less steep, right? And then if I'm to pick any point, maybe somewhere there, let's say t2, pick a point there, this now becomes steep. This is now steep. So what it means is that the acceleration at t1 is actually greater than the acceleration at t2. So this is still non-uniform acceleration, but it's increasing. It's going up. So we must be able to differentiate between these two. The curve is the one that gives us a clue that we have non-uniform acceleration. From those previous graphs, we had a straight line. So a straight line is the one that tells us we have constant acceleration. So I've seen many questions in many papers where they ask you to describe how the graph is actually showing us that we have deceleration, non-uniform acceleration, or uniform acceleration. So you actually have to highlight the nature of the graph. Is it a curve or is it a straight line? If it's a straight line, it means we have constant acceleration. If it's a curve, that means we have non-uniform acceleration. Right, this also leads us to the idea of non-uniform deceleration. Okay, so if we have a curve like this, right, this is speed in meters per second, and then this is time, the side in seconds. This is non-uniform acceleration. Non-uniform deceleration, sorry, non-uniform deceleration. But how does this deceleration look like? I realize there it's a little bit less steep and it's getting more steep. So it was decelerating slowly, less up there, and then later on the deceleration was like just at once. Right, and then for the second one I can have something like this. It is still deceleration, good people. This is still deceleration. The speed there in meters per second, and then this is time in seconds. Again, both of them, this is non-uniform deceleration. This one, at this particular point, there's a steep curve there and then less steep there, so you know what to say at those points. All right. Okay, that's the first part that we need to understand when it comes to the description of motions of on a speed time graph. Okay, make sure now when a question comes, normally it's not in a simple like that. Right, let me give you an example, a more realistic example. Let's say I have a graph like this. Right, this is speed in meters per second. Then horizontally I have time in seconds. Right, I'll start from here, go up, then like this, and then I'll just go straight down like that. Super. So what happens normally, we put some values of t there, so I'll just put t1 at this point, and then I'll put t2 at this point, then I'll put t3 at that particular point. This is 0, right? And then maybe I can put v there. These will be represented by numbers. So when you're describing motion, you don't describe motion at once. You have to split your graph into different portions. For example, you can say from t1, so t equal to 0 to t equal to 1, right? T equal to t1, obviously to be a value there, maybe 4 seconds or something. Or let me put values. Let me say you have 4 seconds here, and maybe 9 seconds, and then 12 seconds. I have 13 there, up there. So from t equal to 0 maybe to t equal to 4, we can omit this t1 there, to t equal to 4 seconds, 0 seconds there, right? The object, you can say the bus, the car, whatever is being highlighted there, right, is moving with a constant acceleration. There is constant acceleration since it's a straight line. You get your 1 mark there. And then when it comes to the second part, you can say from t equal to 4 seconds to t equal to 9 seconds, right? The object is moving with a constant speed. That's when I say it with 0 acceleration there, okay? Because the speed is not changing there. 0 acceleration. And then finally, there's a curve there. If you check, this one is a curve. So if it's a curve, then it means there is non-uniform deceleration there. So from t equal to 9 seconds to t equal to 12 seconds, the object is moving with non-uniform deceleration. Right, perfect. That's how you describe motion actually. Simple as that. Portion by portion, make sure you split your graph into different segments, and then you can get all your 3 marks or 4 marks depending on what the examiner is looking forward to. Right, besides the description, of course, you come across questions that will ask you to find, so finding total or distance traveled on a speed time graph. Distance traveled, right? So the distance traveled on a speed time graph is calculated by, right, distance equals area under the graph. Okay, so your task is to check the type of shape, the type of shape. And in most cases, the types of shapes that we come across are the triangles, right? Triangles, right? You know, triangle is calculated by half BH, right? We have trapezium, right? The trapezium mostly is half A plus B times the height. And of course, you have a square, which is side times side, with a rectangle, which is length times width. So these are the shapes that we normally come across when we are calculating the distance traveled. Please avoid this guy. Avoid this guy. I know people like this formula a lot. Distance is equal to speed times time. Not in physics, guys. At all cost, make sure you avoid this, especially when you're dealing with speed time graphs. Don't use that formula. Any question which asks you to deal with distance on a speed time graph, it's area under the graph. For instance, let's say I have a graph like this, right? This is speed in meters per second, and then I have time on this side in seconds, right? So if it happens that maybe I have an object which was traveling and then with a constant speed there, then suddenly went to rest. If I'm to be asked to find the total distance traveled during this time of motion, it means that I'll have to check what type of a shape do I have here. This is definitely a trapezium, right? Trapezium, right? So remember, we need the parallel sides. So this is going to give us the A part, and this one will give you the B part, and of course this part is going to give you the H values. So we have different situations. So most of the times you just have to make sure that you calculate the area under the graph, and please don't make mistakes.